If you fired a bullet the moment the first anatomically modern human being drew breath on the African savanna, 100,000 years ago, the fastest bullet ever made, leaving the barrel at nearly 1 mile per second, it would not yet have reached the nearest star, not even close. It would still be drifting in the cold dark between our sun and Alpha Centauri, less than 2% of the way there, surrounded by nothing, going nowhere meaningful for another 5 million years. Sit with that for a moment. Let it land. We talk about the stars as if they are our neighbors. We name constellations as if they are furniture in a room we share. We have sent spacecraft beyond our solar system and called it a voyage to the stars. But Alpha Centauri is 4.24 light years away, and a light year is not a year at all. It is a distance. The distance light travels in 1 year moving at 186,000 miles per second, and in a single year light covers nearly 6 trillion miles. So the nearest star, our closest cosmic companion, sits 25 trillion miles from where you are sitting right now. And that is the nearest one. That is the one right next door, astronomically speaking. The Milky Way itself is 100,000 light years across. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light years away. The observable universe stretches 93 billion light years in every direction from Earth. These are not poetic exaggerations. These are measurements made by human beings with telescopes and mathematics and extraordinary patience. And what they tell us, what they have been quietly telling us for a century now, while we have been busy imagining alien visitors arriving in silver discs, is something that should fundamentally change the way we think about who might be out there and whether they could ever, under any physical law we understand, reach us. They cannot, and I want to explain to you why. Not to diminish the cosmos, never that, but because the truth of it is so much more astonishing than the comfortable fantasy we tell ourselves. Let us start with speed. We think we are fast. We have broken the sound barrier. We have placed human beings on the moon. Our fastest spacecraft, the Parker Solar Probe, now moves at roughly 430,000 miles per hour in its closest solar approaches, the fastest object humanity has ever made. It is genuinely remarkable. It represents centuries of accumulated physics, engineering, sacrifice, and ingenuity. And yet, at that speed, which no human being has ever traveled and which would kill you from radiation exposure in short order, it would take roughly 6,500 years to reach Alpha Centauri, 6.5 millennia, longer than all of recorded human civilization from the first cities of Sumer to this moment. The Voyager 1 spacecraft, launched in 1977, is now the farthest human-made object from Earth. It is in interstellar space. We built it and we launched it, and we are rightly proud of it. It is moving at about 38,000 miles per hour, which sounds extraordinary until you understand that it is moving at roughly 0.006% of the speed of light. At that rate, it would take 73,000 years to reach Alpha Centauri, if it were headed in that direction, which it is not. So why is this a barrier? Why can't we simply build something faster? Why can't some civilization, ancient and advanced beyond our imagining, just build a ship fast enough to cross the void in reasonable time? Because of a man named Albert Einstein and a set of equations he worked out in 1905 and again in 1915 that have proven themselves right against every test we have thrown at them for more than a century. Einstein told us something about the nature of space-time, about the relationship between matter and energy and velocity, that at first seems like a technicality and reveals itself, upon reflection, to be the most consequential physical fact in the universe. Nothing with mass can reach the speed of light. Nothing. And as any object with mass accelerates toward the speed of light, the energy required to accelerate it further increases without bound. It approaches infinity. This is not a limitation of our technology. It is not something we might engineer our way around given another 1,000 years of progress. It is written into the structure of reality itself. Special relativity is not a hypothesis. It is among the most experimentally confirmed theories in the history of science. Every particle accelerator on Earth confirms it every day. When we push electrons to 99.99999% of the speed of light in places like CERN, we see exactly what Einstein predicted. The energy required to push them even a fraction faster becomes enormous, then prohibitive, then. as you approach that final fraction of a percent, effectively infinite. Consider what it would take to move even a modest spacecraft, say 1,000 tons, which is far less than we would need for a multi-generational voyage or even a well-stocked expedition, to 10% of the speed of light. That is a reasonable target, the kind of thing you might imagine a sufficiently advanced civilization attempting. At 10% of light speed, a trip to Alpha Centauri would take about 42 years. Uncomfortable, but not inconceivable for a long-lived species with the right life support. The energy required to accelerate that 1,000-ton ship to 10% light speed using the most efficient reaction drive theoretically possible, where you are converting matter directly to energy, which is what E equals mc squared permits, is roughly equivalent to 500 times the total annual energy consumption of the entire present-day human civilization. Every power plant, every solar panel, every burning barrel of oil, everything, multiplied by 500 for one ship, one trip. And that assumes perfect efficiency, which thermodynamics has some strong opinions about. And we have only gotten to 10% of light speed. We are not talking about approaching light speed, where the relativistic effects become overwhelming, where time begins to dilate in earnest, where every further increment requires exponentially more energy. We are talking about 1/10 of the way there. And already the energy budget is almost incomprehensibly vast. But say a civilization could do it. Say they have mastered fusion, or antimatter propulsion, or some energy source we have not yet discovered. Say they solve the energy problem. Then what? Then the interstellar medium introduces itself. Space is not empty. We use that phrase, the emptiness of space. But it is an approximation, a convenience. Between the stars, there are gas molecules, dust particles, cosmic rays, a thin plasma of hydrogen and helium that becomes, when you are moving at a significant fraction of the speed of light, an extraordinarily lethal radiation environment. At 10% of light speed, a hydrogen atom in space becomes, from the perspective of a ship moving through it, a particle with the energy of a cosmic ray. And there are enough of these particles in interstellar space that the radiation dose on the crew of such a ship would be fatal within weeks, perhaps days, depending on shielding. The shielding required to stop this would have to be extraordinarily thick: lead, water, rock, some combination, adding enormous mass, which requires more energy to accelerate, which requires more fuel, which adds more mass, which requires more energy, in the vicious cycle that Konstantin Tsiolkovsky first described mathematically in 1903 and which has haunted every rocket engineer since. It is called the Tsiolkovsky Rocket Equation, and it is the quiet nemesis of every interstellar dream. And we have not yet discussed time. We have not discussed what it means, biologically, to spend decades or centuries confined in a spacecraft, unable to land, unable to breathe real air, eating recycled nutrients, drinking reclaimed water, with a skeleton losing density in the absence of proper gravity, with a cardiovascular system that evolved to pump blood against Earth's pull, slowly failing in weightlessness, with a psychology shaped by millions of years of open horizons and social groups of 50 slowly unraveling in an enclosed metal tube. We study this on the International Space Station. We have seen what 6 months does to a human body. We extrapolate with genuine concern what years would do, what decades would do. Some people invoke suspended animation, and it is a seductive idea, but it is not biology. We do not know how to safely arrest human metabolism for years or decades. We know how to cool certain tissues briefly for surgery. We know that some organisms can endure extreme desiccation and revive. But the mammalian brain, with its intricate electrochemical architecture, is not a seed. It is not a tardigrade. Every attempt to freeze and revive complex neural tissue results in ice crystal formation and cellular destruction. We might someday solve this. Perhaps. But it is not a solved problem, and we must not pretend it is when we are being honest about what the physics actually allows. Now let me say something clearly, because I want to be fair to the grandeur of the cosmos. The laws of physics that we know are the laws of physics we have discovered so far. There is always the possibility, and it is a genuine possibility, not a dismissal, that some deeper physics exists that permits what we call shortcuts. Wormholes are mathematically possible in general relativity. Alcubierre's warp metric is mathematically self-consistent. These are real solutions to Einstein's field equations, not science fiction inventions. But wormholes, as they appear in the equations, require negative energy density to remain open. Exotic matter with properties we have never observed and have serious reasons to believe cannot exist in the quantities required. Alcubierre's warp drive requires a mass energy equivalent roughly equal to the mass of Jupiter, structured in ways that may be fundamentally unphysical. We are not forbidden from dreaming of these things. But honesty requires us to note that dreaming is different from doing, and that every extraordinary claim about faster-than-light travel carries an extraordinary burden of physical explanation that, as yet, no one has met. And so we arrive at something that Enrico Fermi asked one afternoon at Los Alamos in 1950, in a conversation that has reverberated through astrophysics and cosmology ever since. They were talking about alien intelligence, about the probability of life elsewhere in the universe, about whether extraterrestrial civilizations might have already visited Earth and Fermi, with the characteristic directness of a man who had helped create the first artificial nuclear chain reaction. Asked a simple question: where is everybody? If intelligent life is common in the universe, if civilizations arise, as we suspect they might, wherever the conditions are favorable and given enough time, and if interstellar travel is possible, even for a fraction of those civilizations, then the galaxy should be, by now, thoroughly colonized, or at least thoroughly explored. The Milky Way is 10 billion years old. Even at the crawling pace of our own best technology, a few percent of light speed over thousands of years, a civilization that started spreading from its home star a billion years ago should have reached every star in the galaxy long before our solar system was even born. And yet, nothing. No signals we can identify, no megastructures, no probes, no artifacts, no visitors. This is the Fermi paradox, and it is one of the most disturbing unsolved problems in science. There are many proposed solutions. Perhaps intelligent life is vanishingly rare. The great filter hypothesis. Perhaps civilizations destroy themselves before they can spread. Perhaps they go quiet, turning inward into simulation or virtual existence. Perhaps the universe is genuinely, heartbreakingly empty of other minds. Each solution carries its own weight of wonder and terror. But one resolution to the Fermi paradox that is not discussed enough is simply this: perhaps interstellar travel is so difficult, so expensive, so demanding of energy and time and biological endurance that it is not something civilizations do. Perhaps the distances are genuinely prohibitive for biological beings. Perhaps the universe is full of intelligence that burns bright on its homeworld, reaches out in radio waves and light and mathematics, and then simply stays. Because the distance is too far, and the cost too great, and the biology too fragile, and the physics too unforgiving. This is not a defeat. I want you to hear that. This is not a defeat. Because here is what it means. It means the Earth is our home in a profound and non-negotiable way. Not as a sentiment, not as a slogan, not as something you put on a bumper sticker. As a physical, cosmological, biological reality. We evolved here. Our bodies are calibrated to this gravity, this atmospheric pressure, this particular blend of nitrogen and oxygen, this 24-hour rotation, this intensity of sunlight at 93 million miles from a G-type main sequence star. We are not a species that can simply pick up and go somewhere else. We are not travelers who happen to be staying at Earth right now and might check out and move to a nicer planet when the mood strikes. We are the Earth, in a very real sense. We are what the Earth does when it gets sufficiently complex and starts wondering about itself. I think about this often. I think about the people who lived their entire lives on the same square mile of ground, who knew every tree, every stone, every seasonal variation in the light, and who loved that ground with a depth that people who move every few years perhaps do not fully understand. And I wonder if we are that cosmically, if we are the beings whose square mile is this solar system. If everything we will ever be and ever do and ever discover and ever create will happen in this small, warm corner of an unremarkable galaxy. And I find, to my surprise, that this does not diminish me. It concentrates me. It focuses me the way a lens focuses light into a point of extraordinary intensity. Carl Friedrich Gauss, in the early 19th century, imagined drawing enormous geometric figures in the Siberian snow, visible from space, to signal our presence to possible inhabitants of other planets. He could not have known what we now know about the distances involved, but the impulse, that beautiful, desperate, characteristically human impulse to reach out, to say, I am here, to connect. That impulse is real, and it is worth honoring. We have been reaching out. Frank Drake, in 1960, aimed a radio telescope at two nearby stars and listened. He heard nothing, but he did something more important. He asked the question formally, scientifically, with instruments and patience and rigor. He and his colleagues later devised what we call the Drake equation, an attempt to estimate the number of communicating civilizations in our galaxy, which is not an equation that gives you a precise answer so much as it is a structured meditation on our ignorance. A way of organizing what we do not know, of identifying which questions we must answer before we can even begin to guess at the answer to the big one. Are we alone? We do not know. And that not knowing is one of the most honest and important and wonderful things about the current human condition. Here is what we do know. We know that in 1992, Alexander Wolszczan and Dale Frail discovered the first confirmed exoplanets, planets orbiting another star. We now know of more than 5,000 such planets, detected through the Kepler Space Telescope and TESS, and ground-based observatories using methods of breathtaking cleverness. Tiny dips in starlight as a planet transits its sun, minute wobbles in a star's radial velocity caused by the gravitational tug of an orbiting world. The universe is full of planets. Many of them are rocky, many of them orbit within the habitable zones of their stars where liquid water is plausible. Some of them may have atmospheres. Some of those atmospheres may contain oxygen. Not certain, not proven, but possible and searchable. We know that life on Earth arose relatively quickly after the planet cooled enough to support it. That simple chemistry gave rise to self-replicating molecules, that those molecules gave rise to cells, that cells gave rise to multicellular organisms, that organisms gave rise to nervous systems, that nervous systems gave rise to this room, to you, to me, to the question I am asking you to sit with tonight. That journey from chemistry to consciousness took roughly 4 billion years, which sounds like an eternity until you consider that the universe is 13.8 billion years old, and there were stars forming planets long before our sun ignited. There was time. There was, and there is, an enormous amount of time. So life may well be out there. Intelligence may well be out there. Other minds, other histories, other ways of experiencing the cosmos. They may be real somewhere in the unimaginable vastness of what exists, but they are not coming, not to us, not across those distances, against those energy barriers, through that lethal radiation, for those spans of time. The physics does not permit it for biological beings. And whatever we might imagine for post-biological intelligences, for minds uploaded into machines, for von Neumann probes that self-replicate across the galaxy. We have no evidence of any of these things, and imagination, however wonderful, is not a substitute for evidence. What this means for how we should live. That is the question I want to close with, though I am reluctant to close because this conversation feels to me like one worth having in very long form, over many nights, with wine and patience and a willingness to sit with the uncomfortable alongside the beautiful. We are alone in our solar system, almost certainly. We are perhaps alone in our region of the galaxy. We may be in contact, someday, with other intelligences by the only method the physics permits across interstellar distances. Light, radio waves, the electromagnetic spectrum, messages, not visitors. The universe as a library, not a neighborhood. And the messages will take years or centuries to arrive, and years or centuries to answer, making conversation in any conventional sense impossible. What we will have instead is the transmission of knowledge, of art, of mathematics, of history, of the strange and specific experience of being alive on one particular world. And that is worth having. That is extraordinary. That is a form of contact so different from what our science fiction has imagined that we have not yet fully come to terms with it. We have imagined meetings, handshakes, trade, war. We have not fully imagined what it would mean to receive, in a single transmission, the complete recorded knowledge of a civilization that arose 1 billion years before ours on a world we will never see. But let me come back to Earth, literally, because I think that is where the most important thing lives tonight. If no one is coming to save us, then we must save ourselves. This is not a political statement. It is a physical one. The cosmos is not watching over us. The cosmos does not watch at all in the way we mean when we use that word. With care, with intention, with the possibility of intervention. The cosmos is vast and cold and astonishingly beautiful and entirely indifferent to whether we survive the next 1,000 years. Whether we manage the temperature of our own atmosphere, whether we keep the blue film of air and water and life thin around this small rock habitable for the extraordinary experiment of consciousness that is currently running on it. We are it. We are the only known form of intelligence in the observable universe who is in a position to do something about the future of this planet. The bacteria do not vote. The whales, however intelligent, are not building space telescopes or climate models. We are the only thing standing between this world and the indifferent forces that would, over billions of years, even without our help, eventually render it uninhabitable. The sun will expand. The magnetic field will eventually weaken further. Asteroids will continue to cross our path. We are, in the words of the physicist Freeman Dyson, a man of extraordinary imagination and rigor, the universe's way of taking charge of its own destiny, at least locally, at least for now. That is not a small thing to be. There is a photograph, you know the one, taken by Voyager 1 on February 14th, 1990, at my request, from a distance of about 3.7 billion miles. The Earth in that photograph is a pale blue dot, less than a pixel, suspended in a ray of scattered sunlight, surrounded by the black of space. Everything that has ever happened to any human being happened on that dot. Every king and every slave, every act of heroism and every crime, every love affair, every war, every meal, every prayer, every dream, every moment of wonder and every moment of despair. All of it on a speck of dust suspended in a sunbeam. I look at that photograph and I think about the interstellar distances we have been discussing tonight, and the two images, the distances and the dot, seem to me to say the same thing in different languages. They both say, you are here and only here, and this is everything you have. What the physics I have described tonight says to me, personally, after a lifetime of studying it. It says that the universe is not built for visiting. It is built for existing, in place, for arising, for complexity, building itself up from simplicity over enormous timescales, for consciousness flickering briefly in the cosmic dark, aware of itself, asking questions, making music, loving other conscious beings, and then going out. It is built, perhaps, for exactly this, for a species to rise on a warm, rocky world, to look up, to understand the distances, to feel the loneliness of them, and to find, in that loneliness, not paralysis, but responsibility. Because if we are alone, or if we are effectively alone, separated from our cosmic neighbors by barriers that no biology can cross in any reasonable span of time, then what happens to us is on us. The decisions we make in the next century, the next decade, the next year will determine whether the only known form of self-aware consciousness in the universe persists or doesn't. I do not say that to frighten you. I say it because it seems to me the most galvanizing, true thing I know. The ancient Greeks, who gave us so much of the vocabulary we use to ask these questions. Aristotle, with his first careful attempts to catalog the natural world. Aristarchus, who proposed 17 centuries before Copernicus that the Earth orbited the Sun and was largely ignored for it. Eratosthenes, who calculated the circumference of the Earth with staggering accuracy, using only a stick and geometry and the length of shadows. They did not know about light years or special relativity or the interstellar medium, but they began the project, the extraordinary ongoing human project, of measuring the world, of asking how far and how large and how old, and refusing to accept the comfortable small answers. That project is us at our best, not us building weapons, not us drawing territorial lines on a dot, not us fighting over which particular cultural tradition owns the truth. Us, with our eyes open, measuring shadows and listening to the sky and asking questions that will not return answers in our lifetimes, but that advance the knowledge of our species by another increment, another step along the long walk. Newton, who synthesized the celestial mechanics that let us calculate where every planet in our solar system will be 1,000 years from now, stood, famously, on the shoulders of giants. We all do. Every equation that tells us the nearest star is out of reach was built on other equations, which were built on experiments, which were built on observations, which were built on the simple and ancient human habit of looking up and wondering why. The wondering is never a waste. The wondering is everything. Here is something that moves me very deeply about the physics of interstellar travel. When we say that a signal, a beam of light, a radio wave, can cross the distances between stars while a physical ship cannot do so in any practical sense, we are saying something profound about what can persist and what cannot. Physical matter, biological beings, the soft and complicated machines that we are. We are fragile, perishable, local. But information, patterns, mathematics, music, the structure of a thought or a theorem, these can travel at the speed of light. They are, in a sense, the only things that can. If there are other civilizations out there, separated from us by the very distances that make physical contact impossible, the only bridge is the message. The only meeting place is the electromagnetic spectrum. And what gets transmitted across that bridge is not bodies, but ideas. Not beings, but knowledge. Not presence, but the record of what it was like to be alive, to be conscious, to be capable of understanding the universe, however partially, on one particular world, at one particular moment in the long history of stars. I find that astonishing. I find that, in its own way, more beautiful than the science fiction version. Because what it says is that consciousness, the ability to understand and communicate, is the only thing lightweight enough, energetic enough, fast enough to actually cross the cosmos. The physical is trapped. The conceptual is free. We are, all of us, trapped here on this beautiful dot. The physics says so, clearly and without apology. The distances are what they are. The energy requirements are what they are. The biological fragility is what it is. The speed of light is 186,000 miles per second, and nothing with mass has ever exceeded it, and nothing we understand suggests it ever will. And standing inside that constraint, looking up at the night sky, and knowing that what we see are suns, billions of suns, each one the center of a system, each system potentially harboring worlds, each world potentially harboring the chemistry of life. I am not diminished by the impossibility of reaching them. I am expanded by the fact that we can know them, measure them, understand the nuclear reactions at their cores, trace the elements they have forged, realize that the iron in our blood was created inside a star that exploded before our sun was born. We are made of stellar material, literally. The carbon in your body was fused in the core of a star that lived and died billions of years ago. The calcium in your bones, the oxygen in your lungs with every breath. We did not come to the stars. The stars came to us, not as visitors, not as travelers, but as the actual substance of our flesh and blood. So when I say that the stars are out of reach, I want to be precise about what I mean. The stars as destinations, as places to visit, as locations to plant flags or establish colonies in any meaningful human time frame. These are out of reach. But the stars as origin, as family, as the source of everything we are physically made of, those stars are not distant at all. They are right here. You are carrying them with you. Every atom in your body arrived here by a longer journey than any spacecraft could ever take, and it arrived long before you did, and it will remain long after you have gone, cycling back into the Earth and eventually into the Sun, and eventually, in some cosmically distant future, into the next generation of stars. We are not separated from the cosmos. We are made of it. We are the part of it that has woken up and started asking questions. And the questions, the asking itself, that is what crosses the distances. That is what the physics in its finality leaves us with. The silence between the stars is real. It is vast. It speaks volumes about the loneliness of intelligence in a universe that does not hand out neighbors easily. But the silence is not the end of the story. The silence is the space in which the question lives, warm and unextinguished, passed from one generation of curious beings to the next, carried forward in books and telescopes and equations and the eyes of children who look up on clear nights and ask, without knowing the depth of what they are asking. What is that? What is that? The question that built civilization, the question that sent Galileo to his telescope and Einstein to his blackboard and Drake to his radio dish and every one of us at some point in our lives to a patch of dark ground far from the city lights, staring up, feeling small and enormous at once, part of something we cannot name and cannot reach and cannot stop trying to understand. The nearest star is 25 trillion miles away. No human being will ever stand on any world that orbits it. The laws of physics are not negotiable on this point, and I find that I have made a kind of peace with them. Not the peace of resignation, but the peace of someone who has looked honestly at a hard truth and found that at the center of the hardness, there is something worth holding. We are here, and only for a little while, and the universe, indifferent and magnificent, is watching us the only way it knows how, by being what it is and letting us discover it. That is enough. That, honestly and truly, is more than enough.